During this video, make sure that you have your periodic table handy so that you can jot down some notes on your periodic table about what some of the names are for the different families that we're going to discuss. This particular picture that you're seeing right now in the video is going to kind of share with you some of the names that we have. So the very first family, family number 1, that has lithium in it, those are called your alkali metals. Family number 2 that starts with beryllium, that would be your alkaline earth metals. And then when we skip over to family 15, that one is the nitrogen family. And then 16 is called your oxygen family. 17, those are called your halogens. And 18 are your noble gases. So those are some names that you'll hear mentioned in class. And if you have those labeled on your periodic table, that might be handy. So when we're classifying elements, we need to remind ourselves that families do have similar properties, and one of the properties that they have in common are their valence electrons. And the valence electrons are the electrons in the highest occupied energy level. You did an ExploreLearning.com gizmo where you called Element Builder, and valence electrons was one of the things that it talked about, where you drew dot diagrams. And for instance, lithium has 1 valence electron, so you drew 1 dot around it to represent that valence electron. So that's something that all the families have in common. If you look at your alkali metals, we're going to be calling them, we're going to be adding this A or B here behind the number, and we'll talk about that a little bit later, but that's something that's not on your periodic table, and you might want to put that in there. The alkali metals are 1A, and they are made up of lithium on down to francium. They have 1 valence electron, which means that they all end in S1. So 1s1, 2s1, 3s1, so on. They're very shiny and lightweight metals, and they're very reactive. The most reactive being francium. So the most reactive is at the bottom. And then we have our alkaline earth metals, and these are 2A would be the number that we're going to use for those. And again, that would be beryllium, magnesium, calcium, all the way down to radium. And they have an S2 ending. So they are also in that S orbital. They have 2 valence electrons, 2 dots if we were to draw the dots around the element symbol. They are the second most reactive family. When they're mixed with water, they become alkaline or basic. So if you hear about acids and bases, these would be bases. Radium is a glow-in-the-dark paint. So if you've ever thought about redecorating your bedroom, having some glow-in-the-dark paint probably contains radium. And then we're going to skip to the halogen family. So if we were to count them in order, this would be number 17, but we're going to call our halogens 7A. They have 7 valence electrons, so that's why we're kind of sticking with this 7 for right now instead of 17, but even with the 17, it has the 7 in there. Hopefully that helps you to remember that there are 7 valence electrons. That's a common family trait. The most reactive here is fluorine. This is a very reactive family, the most being at the top, fluorine. So on the periodic table, your most reactive metal is francium. It was in the family 1A at the bottom. And your most reactive non-metal is fluorine at the top of the halogens group. And then we have our noble gases, and our noble gases, we are going to call them 8A, and the 8 would stand for what the valence electrons are for the majority of the group. Now this one doesn't follow the same as far as all of the elements having the exact same number of valence electrons. Remember, helium only has 2 protons, and so it is a full element because the first energy level can only hold a maximum of 2 electrons, and so it's happy and full with those 2. But then starting with neon on down, they all have the 8 electrons around them because it takes 8 to fill up those energy levels. So they rarely react with anything. You'll hear the word inert used. That just means that they don't react. And they do have the highest occupied energy level is full. For helium, it only uses energy level 1, and so that would be S2, since the first energy level only has the S sublevel, but then all the other ones end with P6. Those representative elements that we were just mentioning all have the A. Those are called representative elements. There's a very wide range of physical and chemical properties because 1 and 2A are metals, but 7A is nonmetals. The S and the P sublevels are your highest energy level, and they're not filled up. 1 and 2, 7A, they're not completely full. So for example, lithium, it's not full because the second energy level is missing an electron. You have things like silicone, where its highest energy level is the 3 with the P sublevel, but it can hold a total of 6, but it only has 2. So they're not completely full when it comes to their electron configurations. Now let's take a look at the big chunk of elements that we're going to refer to as our transition metals. And this is what separates our representative elements. So these are going to be 1A, 2A, and then we'll have 3A, 4A, 5A, so on. And then we had 7A and 8A in our notes. Okay, these are going to be B's. So these are going to all end in B's. You'll see some periodic tables that have that on there. Transition metals separate your representative elements. So this big block here in the middle that make up your D orbital, and the 2 that are kind of taken out and put at the bottom that make up your F orbital. Those are all transition elements. The transition metals are the main body, and they are going to be the ones that have the D orbital. So that would be the one here that you see in green. Those are the transition metals. And then you also have the 2 periods that we pulled out and put at the bottom. Those are called inner transition metals. They're still transition metals. We just refer to them as inner transition metals. They make up your F orbitals. Now, if you look at your periodic table, you're going to notice that this one is number 57 and this one is 89. And they actually go right... they would go here and here. This periodic table is not fully complete here. So that's why they're called inner transition metals, because this whole chunk actually fits inside right here, which would push the rest of these over by 14 elements, which isn't very convenient. That wouldn't fit on an 8.5 by 11 sheet of paper. So we pull them out, put them at the bottom, and we call them inner transition metals. The top group, the top period there, number 6, those are called lanthanides, and those are found on Earth, and there's only one in there that's very reactive. So these are your lanthanides. That's the top period. It's period 6. And then the other group, sorry, not the other group, the other period, are called your actinides, and all of those are radioactive elements. You're going to find that's where uranium is, which is probably the most common radioactive element used in nuclear energy, and some are not found in nature. So some of those are man-made elements that we make in laboratories. So again, if you want to label your periodic table as we're going here, this bottom column, bottom period, is going to be called the actinides. To finish us off, this slide is going to look at electronegativity. Now, to be fair, this is part of the periodic table because it's something that we'll be talking about more with the periodic table, but it isn't really something that we're going to practice too much with until we get into elements bonding together. But electronegativity is the ability of an atom, of an element, to attract electrons. And so when they're attracting electrons from another element, then they're going to form a compound and they're going to bond together. So when we talk about bonding, we will talk more about electronegativity. But we can use this to help produce the type of bond that will form. You might have heard of ionic and covalent, which are the 2 most common that we will be dealing with, but we also can break covalent down into polar covalent, non-polar covalent. So we can use electronegativity to help us decide which type of bond. And if you just look at the picture that I have here, you'll be given an electronegativity chart when we get to the next unit and we are using it more with bonding. But you're going to notice that the electronegativity, so in other words its ability to attract electrons, decreases from the top to the bottom. So on here it says that it increases from bottom to top, so by default it decreases from top to bottom. In other words, helium doesn't really have a great ability to attract electrons, hence it doesn't really react. That's why it's a noble gas and it's inert. And the electronegativity also increases from left to right. So we have fluorine being the most electronegative, meaning it can attract electrons, it wants to take electrons from other elements, and it can do so very easily. So this little trend that we have about electronegativity, again we'll talk more about it and how it relates to bonding when we get to the bonding chapters, but because it does deal with our periodic table and it's a trend that we see in our periodic table, I wanted to introduce it with this unit.